Hello, and welcome to the Sleepy Brain Science. Tonight, we are leaving the surface world far behind. We are sinking slowly, gently, past the reach of sunlight, past the place where color fades, down into a realm so vast and so dark that most of it has never been seen by human eyes. The ocean floor is not what many people imagine. It is not a flat and featureless plain. It is one of the most dramatic landscapes on Earth, perhaps the most dramatic, with mountains that dwarf anything on land, valleys that could swallow entire continents, and ridges that wrap around the globe like the seams of a living planet. It is a world of immense pressure, slow fire, ancient memory, and quiet, stubborn life. If these gentle journeys are helping you drift off, I hope you will like, subscribe, or leave a kind word below. It helps other tired minds find their way to Sleepy Brain Science, one sleepy soul at a time. But for now, there is nowhere else you need to be. Let your body grow heavy. Let your thoughts begin to soften at the edges. And as the night settles in around you, come with me, down into the deep foundations of the world. Let us begin. A hidden world beneath the waves. If you could somehow drain every ocean on Earth, the first thing you would notice is how wrong our mental picture of the planet has always been. We tend to think of land as the default and water as the covering, but it is really the other way around. The ocean floor covers more of our planet than all the continents put together. Dry land is the exception. The ocean floor is the rule. That hidden landscape does far more than simply sit beneath the water. It shapes how heat travels through the global ocean. It determines where nutrients rise and where fisheries take hold. It influences where carbon is locked away for thousands of years and where it is eventually released. Even small changes in the deep sea floor can ripple outward and affect the world above in ways that take generations to fully understand. When you picture Earth tonight, try imagining it not as a land planet with oceans in between, but as a water world where the continents are simply the tall places poking above the surface. The longest mountain range you've never seen. Earth has a mountain system longer than any other, and almost no one has laid eyes on it because nearly all of it lies underwater. The mid-ocean ridge is a continuous chain of peaks and valleys that threads through the Atlantic, the Indian, the Pacific, and the Southern Oceans, wrapping around the globe the way stitching wraps around a baseball. In places, it rises more than a mile above the surrounding sea floor. In others, it is split open along its spine by long fractures and steep walls. Some sections are broad and gently rounded. Others look raw and torn. Along its crest, volcanic rock is constantly being born. New material rising, cooling, and then slowly drifting outward as more rock pushes up behind it. The ridge also acts as an enormous obstacle for deep ocean currents, redirecting them through gaps and passes in ways that matter to the chemistry of the water far above. On a map, the mid-ocean ridge looks like a living seam, evidence that the planet is still actively rebuilding itself, quietly in the dark. Where new Earth is being made. There are places on the seafloor where the planet's crust is being pulled apart, As two plates separate, the material below grows thin, then opens. Hot rock rises into that space and meets the cold ocean water above it, cooling almost instantly into fresh basalt, a dark, dense volcanic rock that forms the foundation of the ocean floor. This process repeats steadily, pushing older crust outward on both sides of the ridge, the way a slow conveyor belt might carry objects away from a central point. Over millions of years, this creates a clear age pattern across entire ocean basins. The youngest rock sits closest to the ridge crest. The oldest lies farthest away, out near the edges. It is creation with a rhythm rather than a single dramatic event. New seafloor assembled in patient, continuous bands, then carried away into the dark to live out its long geological story, inch by quiet inch. The deepest places on Earth. At the edges of some ocean basins, the seafloor does not simply flatten out. It plunges downward into long, narrow trenches, curved scars in the planet's surface where one tectonic plate is slowly bending beneath another. These trenches are the deepest places on Earth. Their walls can be steeper than many mountain faces on land, and their floors sit so far below the surface that the tallest peak on land could be placed at the bottom and still be completely submerged, with room to spare above. They are not empty places. Sediments accumulate there in thick layers. Rock is folded and fractured by enormous pressure. Cold, dark water collects at the very bottom, and life, patient, adapted, astonishing, finds ways to persist. Every dive into a deep trench is a journey into conditions that our intuitions simply are not built to grasp. Mountains that never became islands. Not every underwater volcano breaks the surface. Many rise from the seafloor in long, solitary eruptions, building themselves upward through repeated lava flows over spans of time that are difficult to imagine, and then stopping just short of the world above. These seamounts are scattered throughout every ocean basin. Some are tall enough to redirect currents passing over them, concentrating nutrients and drawing marine life upward in swirling columns. Others are remote and rarely mapped, which is why researchers still occasionally discover previously uncharted ones during survey expeditions. Their slopes can be coated in slow-growing deep-sea corals that are centuries old. Their flanks can carry the scars of ancient underwater landslides, and the rock inside each seamount holds a record of the volcanic processes that built it, a geological diary written in lava and preserved in the dark. Life where life should not be. At great depth, the pressure of the water above becomes a physical force unlike anything most living things can survive. It presses inward from every direction, distorting the shapes of proteins, disrupting the membranes of cells, and pushing biochemistry to the edge of what is possible. And yet, life is down there, not hiding at the margins, but living fully, feeding, growing, reproducing. The organisms that thrive in the deep ocean have not simply tolerated these conditions, they have been shaped by them over vast stretches of evolutionary time.
Their membranes remain flexible where ordinary ones would stiffen and shatter. Their proteins hold their shape under pressures that would unravel most biochemistry. Their metabolisms are calibrated to stretch scarce food across long, cold stretches of time. The surprise is not only that life exists in the deep ocean, it is how thoroughly life has claimed it.
Maps drawn from hints. Most of the seafloor has never been directly seen. This is one of those facts that can feel hard to believe in an age of satellites and instant information, but it is true. The deep ocean floor is in many ways less well known than the surface of the moon. Direct observation from submersibles covers only a tiny fraction of the total area. Instead, our maps are assembled from indirect evidence, the way sound waves travel through water and reflect off the bottom, subtle changes in the height of the ocean surface that hint at ridges and trenches far below, and careful measurements gathered by research ships crossing the same regions again and again. The result is something closer to a sketch than a portrait across large portions of the ocean floor. Entire regions are known only in broad outlines, which means genuine discoveries are still waiting, sometimes not far from familiar coastlines that have been sailed for centuries. The ocean floor as a time capsule. Far out on the abyssal plains, beyond the ridges and trenches and seamounts, sediment settles on the sea floor in a slow, continuous fall. Tiny shells from organisms that lived and died in the water above. Dust carried by ancient winds from distant continents. Mineral particles formed by chemical reactions in the deep water itself. Layer by layer, year by year, century by century, these materials accumulate, and in doing so, they record the world above them. When scientists lower a hollow tube into the sediment and pull it back up, they retrieve a vertical column of time. The youngest layers sit at the top, the oldest at the bottom. Changes in chemistry within those layers can reveal shifts in ocean temperature, in ice coverage on land, in rainfall patterns, in the paths of ancient currents. Some layers carry the traces of events that happened thousands of miles away and thousands of years ago. The ocean floor is not passive, it remembers. The flattest places on Earth. Far from the ridges, in the widest and deepest parts of the ocean, the seafloor eventually levels out into what are called abyssal plains, and some of these are among the flattest natural surfaces anywhere on the planet. Their smoothness is the result of that same slow, patient rain of sediment. Over long periods of time, fine particles settle evenly across the deep floor, filling in low spots, smoothing over rough edges, and gradually leveling out topography the way a light snowfall softens the angles of a landscape. In some places, the result is so flat that a difference of just a few meters in height across many kilometers of distance is enough to qualify as a notable feature. A small volcanic rise can stand out the way a single hill would stand out on a frozen lake. These abyssal plains are reminders that the deep ocean is not only wild and dramatic. In places, it is extraordinarily precise.
the engine that moves continents. The sea floor is not a passive foundation for the water above it. It is one of the primary engines of change on the surface of the planet. As tectonic plates move, they carry the continents embedded within them, nudging land masses together or pulling them apart, opening ocean basins and eventually closing them, building mountain ranges where plates collide and drawing volcanic chains along subduction zones. Much of the driving force behind this motion comes from the sea floor itself. As old, dense ocean crust sinks back into the mantle at subduction zones, it pulls the rest of the plate along behind it. This sinking motion influences the pace and direction of plate movement around much of the globe. The shapes of the continents, the locations of island chains, the alignments of deep ocean trenches, all of these reflect the long history of sea floor movement. The ocean floor is not scenery, it is the mechanism behind the scenery.
Rift valleys at the ridge crest. Where sea floor spreads apart more slowly, the process is less smooth. Instead of a gently rounded ridge crest, the surface can fracture open into a deep central valley, a rugged, torn-looking trench sitting at the very top of an underwater mountain range. This happens because the crust is being pulled apart faster than volcanic rock can reliably fill every gap. The surface breaks and drops, creating a staircase of faults and displaced blocks that expose rocks from deep inside the oceanic crust, layers that are rarely seen anywhere else. These rift valleys are also some of the most geologically active places on the seafloor. Cold seawater seeps down through the cracks in the rock, heated by magma below, and returns to the ocean transformed, carrying minerals and heat that feed the remarkable ecosystems found along the ridge. Flat-topped mountains and drowned shorelines. A guyot is an underwater mountain with a flat top, and that flat top is a story. Every guyot began as an island. At the surface, where waves and weather have power, the top of a volcanic peak is gradually worn down into a broad, level platform. Then, over time, the weight of the volcano presses the ocean crust beneath it downward, and the whole structure begins to sink. That flattened summit descends slowly, away from the reach of sunlight and waves, carrying its ancient platform into the deep. What remains is something that looks almost sculptural, a mountain with its crown removed, sitting far below the surface, preserving the shape of a shoreline that may have formed millions of years ago. Chains of guyots can stretch across an ocean basin, each one marking a different chapter in the journey of a tectonic plate, a row of drowned islands, each one lower than the last, telling a story of motion and time. The conveyor that recycles the seafloor. Where subduction zones exist, earthquakes are never far away, and some of the largest earthquakes ever recorded have begun on the seafloor. The process builds slowly. Where two plates are locked together along a subduction boundary, stress accumulates over years, decades, sometimes centuries. The plates keep trying to move, but friction holds them in place. Eventually, the accumulated strain overcomes the friction holding things together, and the seafloor lurches suddenly, releasing energy that can travel across an entire ocean.
When that sudden displacement occurs in the right geometry, it can generate a tsunami, a series of waves that carry the energy of that rupture to distant coastlines. The speed and scale of such events can be staggering. Scientists study these boundaries carefully, using seafloor instruments that track tiny tremors, measure slow deformation, and listen for changes over time. The goal is to better understand how stress builds, because these earthquakes are not random events. They are the inevitable release of forces that the seafloor has been quietly accumulating all along.
The seafloor reads Earth's magnetic history. Long before anyone visited the deep ocean in person, ships began detecting something strange in the magnetic readings they took above the sea floor. The measurements would alternate in regular bands, stronger in one place, weaker in another, repeating in a pattern that looked almost like a barcode. The explanation turned out to be extraordinary. When volcanic rock cools, the iron-bearing minerals inside it become magnetized in the direction of Earth's magnetic field at that moment, like tiny compass needles frozen in place as the lava hardens. Over geologic time, Earth's magnetic field has reversed many times, and each reversal leaves a new stripe of rock with the opposite magnetic orientation. The seafloor, assembled steadily at the ridges and then carried outward over millions of years, had been recording every one of those reversals in sequence, a continuous magnetic diary written in stone, stored in the dark. Once researchers understood what they were looking at, the ocean basins became a readable archive of Earth's deep past. The planet had been writing its own history all along. Lava that looks like pillows. When lava erupts underwater, it does not behave the way it does on land. The outer surface of the flow meets near freezing water and solidifies almost instantly into a glassy skin. But the molten interior is still moving, still pressurized, and so it pushes outward, bulging through weak spots in the skin, forming rounded lobes that stack against each other as the eruption continues. The result is called pillow lava, and it looks remarkably like what its name suggests, a tumbled heap of dark, rounded forms that look almost soft, though they are solid basalt. Pillow lava is found across vast areas of the ocean floor, and it also appears in ancient rock sequences now exposed on land, a telltale sign that those rocks once formed beneath the sea. Between the rounded lobes, networks of cracks and spaces allow seawater to circulate through the rock, altering its chemistry and creating pathways for heat and minerals to move upward into the ocean above. It is one of the most widespread rock types on the planet, and almost none of it is ever seen. Where chemistry feeds life. In some parts of the seafloor, seawater seeps down through cracks, travels deep into hot volcanic rock, and returns to the ocean entirely transformed. It comes back superheated, sometimes hundreds of degrees, and loaded with metals and sulfur compounds that would be toxic to most familiar life. When this fluid meets the cold seawater above, the minerals it carries precipitate almost instantly, forming dark plumes that look like smoke rising from the sea floor. Over time, these minerals build towering chimneys, some of which can grow several stories tall.
Around these hydrothermal vents, something remarkable happens. Microorganisms use the chemical energy in the vent fluid, not sunlight, as the foundation of a web food. Larger animals, shrimp, tube worms, snails, fish, crabs, gather around that chemical energy, forming dense communities in places where darkness would otherwise seem life impossible. These ecosystems are not borrowing energy from the sun, they're running on the chemistry of the planet itself.
Towers of stone, built and broken. The chimneys that form at the hottest vents, called black smokers, can grow remarkably fast. Minerals precipitate so quickly that a chimney can extend by inches in a matter of days, hardening as it grows, fed by the continuous upward rush of mineral-laden fluid. Inside, the temperature stays high enough to keep the flow moving. Outside, the dark plume billows upward into cold water, dispersing fine mineral particles in a spreading cloud. But these towers are fragile. As chemistry shifts, the plumbing within the rock below can change. Fluids are redirected. Some passages clog, others open. A chimney may begin to lean, crack along one side, and eventually collapse, sending a cascade of mineral rubble across the seafloor around it. That collapse does not end the vent's story. New pathways open in the debris. New chimney growth begins nearby. The neighborhood rearranges itself around the wreckage, and life follows. It is a cycle of construction and collapse, playing out in slow motion, in total darkness, powered by heat from below. The story continues. There is still so much to discover down here. Most of the seafloor remains unmapped in detail. New species are still being found at hydrothermal vents. New seamounts appear on surveys where none were known before. Deep sediment cores continue to reveal chapters of Earth's climate history that were previously unreadable. The deep ocean is not a finished story. It is an ongoing one, slowly written in stone and sediment and magnetic minerals and the patient chemistry of circulating seawater. And every expedition that descends into that darkness comes back with something unexpected. For tonight, though, let the deep settle around you. Let the weight of all that water press gently down. Let the slow drift of sediment and the quiet pulse of the ridge feel like the breathing of the planet itself, steady, rhythmic, ancient, and calm. You have drifted a long way down tonight, and somewhere far above, the surface world is carrying on without you. This has been Sleepy Brain Science. Sleep well.